Test. Test. All right, are the levels coming through okay here? All right, just a few more minutes and we'll get things started. Just getting a few last minute things set up so that we're ready to go. If you want to follow along, we'll be using Binary Ninja as the disassembler along with GDB for a debugger, and I can walk through setting that up real quick at the beginning. All right, I think we can get things kicked off at this point. Close out of this, minimize this. All right, so we're walking through the Lappy challenge from the and not XOR badge from this year. That the CTF just ended, I think, yesterday. I don't have one of the badges, but I was passed this binary to take a look at, and I solved this maybe a few days ago, but last week, and was gonna do it last week, then it got extended, so we're doing it today. Like I said, I've already solved this, so this isn't the first time going through it, but I'm gonna try to stay pretty close to how I originally worked through it, so that you can see the thought process and kind of how I went about doing that, and give you an idea of how I approach these types of problems. And I'll try to point out stuff along the way that's something maybe I take for granted, or is things that I just have incorporated into my workflow that may not be super straightforward. But yeah, I guess we'll get started. I'm going to be using Binary Ninja for this challenge for disassembly. You don't have to do that. There are many tools out there. There are many free tools out there as well. You could solve the entire thing with GDB or any debugger out there, but it generally is nice to have a more full-featured disassembler available to you. It will just make it easier to look through the source or the disassembly and kind of recreate what was actually going on. But I do find that it is helpful when possible to do both static and dynamic analysis, so using both a dead code disassembler like Binary Ninja or Ghidra or R2 or Cutter or IDA, as well as something live like a debugger like GDB. There are some things that are just easier to reason about when you can actually inspect memory, and so we'll be using a combination of the two of those today. I'm going to open this right here. This is the file on my local file system. And if you already have this, you can do the same. But we're going to open this up. This is a brand new database. There's something that's been updated in here, nothing that's been changed. This is like the default state when you load in the executable for analysis. Every tool is going to be a little bit different. You're going to get different output. Right now, I'm looking at the high-level IL interpretation, which is somewhere between a decompiler and a disassembler. In Binary Ninja, you can swap that down here. So change it from say HL, IL to disassembly. I'm not going to use any other options here besides these two. If you're using something like Ghidra or Cutter, you'll have options for the decompiler. Depending on the output of it and how good it does, you'll find that it is hit and miss in terms of quality and how easy it is to kind of follow that, especially for small stuff like this. getting started, like one of the first things that I always do is look up a little bit about the binary. So you'll see here the taco th executable right here. We can use file on it, and this is just going to tell us a little bit about what the executable is. It's a 64-bit shared ELF, dynamically linked, not stripped. So we're going to have symbols, like you can already see here, symbols, which are nice. So gives us a little bit of information. The other thing you may not know is a tool called checksec, which may not be installed. Cool. Let me go ahead and get this into this virtual environment, and we're going to install Pwn tools. And this will give us the checksec binary. Should give us the checksec binary. Wonderful. So it's not going to. That's fine. We'll open this in GDB, and it will give us the information. I'm using a plugin for GDB here called Jeff, similar to like Pwn debug. This is where you can get it. It basically makes like the nice colors and provides a bunch of other functionality for you. Installation's pretty simple. You can grab it from right here and just kind of installs it. Because Pwn debug is similar. It's going to have a lot of the same functionality that you're going to get from Jeff. But the important things to know here is that this is position dependent. And we can see that by looking at the addresses in the disassembler. These are all offsets. So right now, if you look at the base address of the binary is going to be at 0 right here. So this is where the ELF header starts. So when we run this, it's not actually going to start at 0. And one of the things you're going to run into if you're trying to like set a breakpoint, for instance, maybe you want to set a breakpoint on main. So I'm going to go and I'm just going to grab the address here. If we set this, we run it, you're going to notice that it can't set it. And that's because it's not actually being mapped there. One of the things about position independent code is that it's going to let the OS like map it to any starting address it wants to. And so it's going to make it more difficult for you to set that up. One of the nice things is that using GDB, we know where it's going to get mapped. There's a fixed address that it's going to do that, and you can look that up just by Googling it. This is for 32-bit. And you'll find the answer here somewhere. But the quick way to do this is if you just run this, you can use the vmmap command, and this will show you a virtual memory map. And we can see that this has been mapped to this address right here. So this 5555555554000. So you got to make sure that you run this once the program has been run or is running. Otherwise, it won't have mapped it yet, and you won't have valid numbers filled in here. It'll still be the offsets. So I'm just going to grab this from right here. And excuse me, like fumbling around with Windows. I am very new to this. but my laptop, it is a MacBook, is not so great anymore for streaming. I think I can Control C that. And then the thing we're going to do here is we're going to go into our tool, or Binary Ninja, and we're going to hit the rebase button. Any tool that you have should support this. Any good disassembler will. If you're using R2, I believe like the -B flag will do what you need to do. In IDA, there's an option to rebase it. In GDB, when you set up the initial import of the file, you'll have an option to specify your start address. So I'm just going to set this up. You'll see all these numbers now, all these addresses switch. And so it has taken, the starting address of where the elf header is and mapped it to that address. And then everything is offset from there. So now if we go back to main, this address should be sufficient for us to go and actually set a breakpoint. So I'm going to copy this, delete breakpoint, and we'll just set a new one here. And we'll see here we're in main. I'm a little bit past the beginning because I grabbed the address from the HLIL view, but if you go to like the disassembly view, you'll see like this is the instruction that I'm stopped at, and it's the move FS 40 into racks, which is moving I think this is the canary value into racks, so that I can put it on the stack as it sets up main. All right, so we have a working environment. We can set breakpoints. We know what we're doing. Let's start going through and figuring out like what we actually need to do here. I'm gonna go ahead and quit out of here for a minute, and we'll just run this so that we can see what it does. So if we run it with no arguments, we say dfiu only one arg need allowed. Assuming that means only one argument is, or you need more than one argument. So right now there's only one argument specified in for argc argv, which is the name of the binary. We can test this theory and then go and validate it in the code here, but just putting an A in here, and it says fails. So we've made progress. We've gotten past that error message. Going in to here, we'll look at the HLIL for a minute. It's because I think it's easier in some cases to read it, but not in others. Looking at the beginning of the code here, we can skip over this, which is like the canary, and arg1 is the first argument that's getting passed into main. In this case, it's going to be argc. I'm going to go ahead and do some renaming here, which is apparently not the right command. Maybe just n here. Yeah, there we go. So we're going to set that to argc, and this will be argv, and this is going to also update the type, and this is going to end up being that. All right. So it's checking whether argc equals 2. If we pass one argument with it, it's going to equal 2, which is why we get past this fails. So this is the very first check that we're going to do, is right here, and we bypassed that. We found out that we need to have at least one argument with us. There's a whole bunch of stuff here in this else block, and we can likely assume that that like this is the stuff that we're going to end up having to reverse engineer and figure out. But looking around, like we can see, down here, looking at the strings, I think there's actually a view. Yep, for strings. We see fails, and right next to it is success. So I'm pretty sure that we're going to have to find out how to get to like it to print this. So we can go to our cross references here. So this is the string that we're going to want. Let's go find the cross references and see what it takes to get there. So this is the code path that we actually want to get to, is it printing success. There's a whole bunch of stuff here that we need to figure out, but we know we want to get here, and because we know that, there's some tooling that we can use, and I actually spent a lot of time going down this path trying to make it work. Didn't really get very far, and then realized I was using it wrong. But there's a tool called Angr, which is a tool that was written by the Shellfish CTF team as part of CGC. Basically, it's a way to solve constraints about programs. So like, we know that there's input. We know that that input is going to contain, some number of characters, and I want to get to like certain positions, in code. You can, write something that specifies all those constraints, and it will go and try to solve that for you, and then you can spit out like the info for it. I have a script written here to run through that. Like I said, I didn't have luck before, but I made some changes to it, and I'm actually going to spin this up right now and let it run in the background and see if it actually spits something out. Theoretically, it could work, but I don't know how long it will take to run or if it will actually finish. So I'm just going to run this, and we'll let it kind of go in the background. We'll check back on it in a little bit, and I can walk through the code later. But so we know we want to get to here. This is the code path we want to hit. There's some checks here, and it looks like these are shifting us away. If you look at what this goes to, it goes to this. So basically, it's checking all of these to see if they're 0, and if they are, it's going to hit fail. So basically, what we want to do is we want to eventually get to this region of code here, and then we want to make sure that every single one of these x values are going to be non-zero, because if any of them are 0, it's going to jump away from here to the fails. So looking at this from a high level, the general strategy that I'm going to want to take, and probably everyone else is going to want to take if they're doing this, is to figure out how these variables are set, or where they're set. You can double click on these. It will take us into this area where they're set in the BSS segment. And one way to do this is to go and look at the cross references in here. And like I said, this is something you can do in Binary Ninja, but any disassembler will work. Basically, it can take us to the cross references for every single one of these. You'll see like every single one of these likely has only 2 cross references, and the reason for that is that you're going to have one near the bottom, which is going to be the checks here, where it does the comparison if it's equal to 0, before jumping up to the failed area. And then you're going to have, in this case, you have a second check for it here, where it's checking to make sure that this passed. So we have cases where these are being set. Oops. And we have cases where they are being checked for equality. We're going to want to go and track down basically everywhere where that value is getting set, and figuring out how to make that condition true so that we can do it. So if we look through here, we can see that right here, this is the first check that is used to set x 0, 0, and it sets to 1. And going through this, it looks like all these eventually get set to the value 1, which is a non-zero value, after some kind of check. So we have some kind of conditional here, and if the condition is true, then it sets the value. Some kind of condition, if it's true, it sets the value. So on and so on throughout this. So we can go through here. We see a call to fopen, so this is going to open a file on your file system. We'll rename this to FTP or file pointer. It's opening a file called temp, and this is going to be the mode. So whether it's read or write, you can see that this the ASCII representation of this value is W+. We can change the representation of this. Where is that? It should be on. Is it just C? Or A maybe? Yep, it's A. So I'm just going to change these both to R plus and or W plus and R, read plus and write, or write plus, which is append, and read. And then we're going to move back to the code. So you see it fills in the call to fopen, and then it's going to pass this to fputc, which puts a single character. In this case, we're going to pass hex 47, which is display as constant character, the capital G. So we see here that it's writing the letter capital G. We can set a breakpoint here, and we can verify that this is true. We're going to do it right after the calls close, just so we can know that the buffers have been flushed. I'm going to go ahead and open this in GDB again. Set up breakpoint. Sorry, 1 second. Just getting rid of some notifications. Set a breakpoint, and we're going to run it. Right now, we'll just use the letter capital A. But we see our break. I'm going to switch back to the disassembly view, and we're at here. Say move. This is after the call to close. But if we use bang, we should be able to execute shell commands. I'm going to do ls-a, and we can see that there's this temp file that was written here. So we'll cat it out. And we see the capital G was written to here. So we have an idea of what's going on. Switch this back to HLIL for right now. So a little bit. So it's opening a file, it's writing a capital G, and then it's closing it. Nothing super interesting yet, but something to be aware of. We don't really know what this is going to be used for yet, but we'll see shortly. So this is where it starts to make sense to have live debugging, because it will help you kind of understand like what some of this memory points to. It's going to fill in all of these like memory areas on the stack and try to like give them names that are meaningful. But a lot of the time, you're not necessarily going to know like what that corresponds to. So we see that it's calling strcat, and we can let me quit this. Strcat takes a destination and a source, and so it's going to append the source string to the dest string. So it's going to take argv plus 8, which should be the second string. So argv is an array of strings, and in C, strings are just arrays of characters. So this should point to the second element in the array, because pointers in AMD64 are 8 bytes long. So this should point to the second element in the argv array, which will be the second string we're pushing. So in this case, it would be like the A's here. So it's going to append that to var28, which looks to be an empty array. So we can verify that. Let me go to the disassembly and we'll grab we'll grab the address of where this is happening. So what you'll see here is that there's this code that, if you go back to the HLIL, isn't there. And so this is why I think it's really helpful to a lot of the time use the disassembly view, because there's stuff that you'll miss. Hey Gabriel, I have done bug bounties in the past, but I don't typically do them. I work as a red teamer during the day, and just don't particularly want to spend a bunch of time doing bounties for not a lot of money. I haven't had great experiences doing them, and so if there's something interesting that pops up, I'll do it, but it's not like a big part of my time. So like I said, we see here it's copying these 4 bytes into this address on the stack, but if we go back to the HLIL, we don't see that. It's just not there. And if we turn this into a string representation, like we can see these characters, so 67, 61, 6C, 66. These are all printable ASCII. I'm gonna hit these with R, turn it into that. This is the word flag. This I don't think is actually used anywhere, and so it probably the reason it's not shown is most likely because Binary Ninja is smart enough to realize that this is set here, and then it's never referenced again, and so it just kind of eliminated the dead code. And that's a guess on my part. I don't know for sure that that's what it's doing or why. It could be a bug or failed analysis. But yeah, we don't see it here, which like I said, it's one of those reasons why it's really important that you always go and look at the disassembly as well, and get clarity on like what is exactly going on. So I'm going to go back here, and we are going to grab the address of the stircat. I'm going to get it right before we call stircat, and we'll set up a breakpoint. And we'll run it. And we'll see that the values being passed in are, and you'll see there's 3 arguments here, and if you know anything about stircat, you know it takes 2, a source and a destination, like we just saw in the man page. The reason it shows 3 right here is just based on the calling convention of AMD64 on Linux. The arguments are passed in registers. So RDI is your first argument, RSI is your second, RDX is your third. And so GDB is kind of just guessing that that there's 3 arguments here. It doesn't know what this function is or what the prototype is. But because there is a non zero value, and there's a value that is meaningful in RDX, it's just guessing that that the value is meaningful. But if you look here, it's actually the same address here and here. And if we look back at the code here, this was moved into RDX and then from RDX to RSI. And so that's just what the assembled code ends up looking like. And so because RDX wasn't zeroed out, it still has the address here from before it got moved into RSI. So we can ignore this. And as we can see from here, there's a string that's on the stack, and we can verify that it's the stack by looking at the memory map. The stack is these F7s, E2, B0. I think this is, no, where is it? what was it? It was FE2. It's here. It is. Yep. So these are stack addresses. You can see it's allocated for the stack. It's read write, non-executable, just like you would expect from something that has no exec stack. All right, go back to context. So we see that this is our source, this is our destination. It's a zeroed out string. It's just space allocated on the stack. We're going to step in and we're going to go into the strcat method now. I'm going to type spinny, and this is going to step out of the strcat function. And we should have all of our registered save, but I can go back here. We'll grab it from here. This is the destination, and we can verify that that this now contains the string. Copy that. Yep. So it copied that over and did that. So we know that that's happening. We don't know how long this is supposed to be yet. We can try just putting something really long in here. And we actually end up causing a crash. We had a stack smashing detected, which means we overwrote the canary value on the stack. So one of the ways we can figure out roughly how long the input is going to be is by running this until we hit a point where we no longer crash the program. So I'm going to remove some of these. We're still crashing it here. I'm going to delete the breakpoints so we don't keep doing this. Still crashing. So we didn't crash there, but we did there. So we're pretty close. So this is the magic number until we stop crashing. We can see here that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we know it's under 24 characters. We also know that there's going to be somewhat less than that. So 24 characters is the number that stops us from crashing the program. We know that there is going to be a canary value there on the stack, so that's going to be some more characters that we can take away from that. Unless this is at like the very, very bottom of the stack, maybe there's other variables that have been allocated that we need to watch out for. So we roughly know that it's going to be somewhere around like 24 minus 8, which is like somewhere like around 16, is going to be like the number of characters that we can enter. Because any more than that, we're going to start writing into stuff that we shouldn't. So I'm going to switch this back to the HLIL, and we see that we're going to do some checks here. So this is doing sign extend, zero extend. Basically, it's a bunch of really like scary looking stuff that means it's going to take the first character of the string that we just copied, and it's going to subtract hex 30 from it, shift it left by 2, and check to see if it is equal to hex 20, which is 32. So I'm gonna pop open another terminal here and see if this is still going. But yeah, so this died. I think it ran out of memory, honestly. We can check that. Nope, I think the VM is toast. Yeah, that's one of the problems with tools like Angr is they end up using a lot of memory a lot of the time, and so you have these problems where it gets OM'd. We can see forming memory compaction. It is unhappy, but we're back, and let me do that. Do I have Ruby on here? Yep. So we're just gonna get Ruby installed in here so we can get IRB, so we can basically use it as a calculator. So we want to figure out what hex 30 is as a character. So that is the character 0. And if we look at the ASCII table, this is like the start of like the printable like alphanumeric stuff. So we have 0 through 9. We've got some symbols, and then it's like the letters. So basically, what this is doing is it's subtracting off the number that starts at 0, so that we can treat things as an offset from there. So we can do a little bit of math here and figure out like what's going on, but we know that we need to get to hex 20, and so if we do hex 20, let me go back into IRB. Shift right 2. Because it's 8 plus so 56 to CHR, and then we get 8. So to make this true, our first character has to be 8. And we can go back into here into GDB and we can set a breakpoint and we can verify all that, that it actually is comparing the first letter. We're going to do right here. That's not the right thing. I'm going to copy. All right, so I'm going to rerun this, and we're going to end up putting a different value in here. So we want to make sure we're actually pointing at the right thing. So I'm going to do A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. How many letters is this? That's 16, should be good enough for now. We know it's somewhere around like the 16, 17 area, based on what we did before. I'm gonna run this, and we can see this is what we're moving this value into EAX, and this is where all that work is going to get done. If we go back to here, it's moving this the first letter of var 28, and that's what we're looking at here. We're moving it into the X, and this is the move 0 extend. We're moving assign extend. Basically, all this is doing is it's getting us like the first letter, and it's 1 byte. So we're going to set the breakpoint here, and we'll do some looking. We can look at it here just straight up in using RBP minus hex 20. And I forget. I want a byte B. So 41 is A. And our input was A, B, C, D, E. So we know that we're getting the very first byte here. So that gets moved into EAX. We're gonna do the sign extend, and this is just gonna get us the letter A into EAX. So I'm gonna run context again, so we're back here. We'll step forward. See if we can see all the registers now. Yep. All right. So we see RAX has 41 in it. We're going to subtract 30, which was 30 hex, which is what we saw here. We subtract 30, and then we're going to do a left shift by 2. We're going to compare it with hex 20, and then jump not equal to here. So if it's not equal, then we're going to jump to here. And what this is doing is it's jumping over this point, or moving a 1 into this X value, which is the value that we realized that we needed to get set across all of these. So we figured out what the first check is. So let's document that. Just open another terminal. So our input is going to be A, B, C, D, F, E, H, I, J, K, L, M, N, O, P, and I'm going to go ahead and just set up an array here, just so that we can track all of this. A little bit of cleanup to. Oops, why is that? Oh. I don't understand why that's doing that. Huh, maybe it's a Windows thing where it doesn't like that. Anyway, so the first character we know is 8. We just verified that. And the check is at here. Get so let's update this. And we'll copy this. I do really miss having all the nice stuff I have on my Linux stuff. All right, so we're going to rerun this. Actually, let's just keep stepping through this real quick, and we'll see that we skip over that check. We'll see that we're taking the branch because it's not 0, so this wasn't equal. So right here we're jumping to what is this, 5394. Yeah, so we're skipping over this. So that's bad. We're gonna rerun this with the updated value. We're still there, so I'm gonna step. We can do the comparison. We see that Rax has the value 20 in it, so this is now going to be true, and means that we're going to end up not taking that branch, and we're going to stay going down this path right here. So we step here, we see that we are now setting that value, and we're all good. One of the cool things we can also do is, because we know where these are, as we're going, we can check these. So we can see 1, 2, 3, 4, 5, 6, 7, 8. Wait, we can count also. So there's 17 of these. So we can do 17 bytes, and we can grab the address here. And we can check all these. And we can, as we go, check to see that we're setting every single one of these. We know they're roughly done in order. Just like looking through this, we see 0, 0 is set here, 0, 1, 0, 2, 0, 3. So they're roughly done in order. And so we can, as we're going through, we can verify that these are all being set and check that we're doing the right thing. So we've passed the first check, and the next part that we actually care about is down here, because these next 3 get set. We can switch back to the HLIL, and we got to figure out what's actually going on here. I personally think that this is kind of confusing and hard to read, and so I'm going to move us back over to the disassembly. I personally just think that it's easier, but if your decompilation is very good, or you just personally think that's easier to read, go for it. But basically, it has 3 characters that are getting initialized. I don't know exactly how it doesn't really show you how those values get put in there, which is why I think it's confusing. But we're going to move up to here. So we see that the value 43 is moved into RBP minus hex 60. So this is going to be 43 is, I think, C or something. BEC. C. So we're moving 43 into here. We are moving 0 into here, 0 into here, 4 into here, 41, which is A, into here, and 54, which is, excuse my terrible math, T. So we're then moving RBP minus 1F to var 27. And we can go and we can verify what this is. So these are actually safe to reference because the RBP isn't changing. So even though we're not at this line, we can see what that points to. So I'm just going to go ahead and look at that. RBP minus 1F. 7 1F. which is B. So this points to B, which is the second character in the input that we specified. So it's moving that into EAX, and this is moving a full quad word into EAX, I think. And then, or sorry, this is going to get us basically just the first characters, or just that B. And then we're going to XOR that value with what has been put into hex 60, which is 43, which is C. And then we're going to compare what is here with that value. So second letter is getting moved into there. We're XORing it with the value 43, and we want it to equal 4. So again, this is just like some simple math we can do. We need to figure out what the correct value for that B should be such that it equals 4. So I'm just going to go back to here, and we'll just kind of like do this manually. So we want it to equal 4. 1, 2, 3, 4. 1. We want it to equal 4. And we know that we're going to use 43. So what is the value that we need to specify up here to make, when you XOR this equal to this? So if you know the XOR operation, we're going to need to use 0, 1, 0, 0, 0, 1, 0, 0. So we need it to be, what is that? That's 44. So then if we go back to here, we can check out what 44 is. Is that right? Let me just make sure that this is correct. I don't think this was the right answer. So 43 XOR against that, and it should equal. Oh. My bad. Yeah, so it's not. No, it is, yeah. Okay, so yeah, it should equal 4. So this is all right. So 0, 0, 1, 0. All right. I believe this is wrong, but we'll come back to that in a second. But we should be able to verify this, because if we end up being wrong here, it will jump to down here, which bypasses the stuff here. So let's just go ahead and replace this. I'm going to copy, delete breakpoints, and we're going to get basically this. Actually, we'll set it right here. This is where the interesting stuff starts happening. So we're going to set a breakpoint, and we're going to run all right. So we're there. We're going to move everything into EAX. So we see 44 is in EAX. And then we're going to XOR RBP minus 60. (43), which is what we said right here. And like I said, yeah, we did the math wrong because the comparison here of what's that 54, which should be 4, is wrong. So we're off by 3, which is what I thought we were. Oh yeah, yep. That's it. XOR. And yep, there we go. So this should be 40, 4, 5, 6, 7. So 47, which is G. Cool. So let's we'll fix this up here. And we'll redo this real quick. Oh, whoops, that's not the right screen. We're going to make this a G. And we're going to do a comparison. RAX is in fact 4, so we're going to do the comparison here, and it's going to succeed. We are not taking the branch, and we're moving on to the next check. The next check here is it's going to move 1 RBP minus 1E, which we can check out what that is. That's 43, which is C, which should be, so that should be the 3rd character in our string. We're moving that in, doing the same thing. We're checking what's at 5C, which is 0. So XORing it against 0, and we're going to compare it with the value 41. So move back here, and 41. Sorry, it's 4, 1. And we're XORing it with 0. So we need to get it to be 1. So that should be 41, which is A. I'm going to go up here and just fill in this since we know what it is now. So this should be 41. Let's go back. 41 is A. Let's go back and we'll restart it. And actually, let's delete the breakpoints. I'm going to break right there. All right, so we are moving this in. We're moving step, step, step. We do the XOR there, and we are comparing with what is in RBP minus 50, which is 41. We are going to do the comparison. We are not taking the branch, which is good. It means that we are correct in our assumption here, and we're good to go. So we figured that out. Next one is A. And we're looking at the next one here. Let me update the string here too. Then the last one of these we're doing is 1D, which is var 25. I think we can assume at this point that the next one is just going to be the fourth letter that we're looking at. We're moving it into EAX, getting the first letter. We are going to XOR that with the value 0, and then we're going to compare it with what is in for C, which is 54. So we want 54, so it's going to be 1, so we need it to be 0, 1, 0, 1. Yep, so the last letter should be T. So we're going to go ahead and verify that. We'll delete the breakpoints. And we'll just set it right there. Shit. Direct comparison, we're not taking the branch, so we are all good. We're going to move the ones back in, and we can verify this, like I said before, with X. Yep. So we've got 4 of these checks done now. I think these are actually quad words and they're not bytes, which is why it's spaced like that. They're just double words. Was it W? Yeah, there we go. So the first 4 are all set now. That comparison is done right there. Cool. So 8 gat are the first 4 characters that we need to do. So moving on, we're following through to here. We can move back to the HLIL to kind of get an idea of what's going on. So yeah, like I said, I guess you would know that like these are referring to the characters that are like the individual letters of the argv 1 because or what was stircatted based on the fact that they're incrementing from here, and like I guess this if we just changed this to an array of 17, something like that. Does that make it any easier to figure out? Yeah, so I guess that's how you'd figure that out. Is you would set that up correctly, and then it would populate it for it, and you could just see that it was indexing those individual values. Okay. So we've done these. We're now moving into this, and we're going to get the fifth character here. And we're going to A2I the fifth character. We're going to add 1 to it. So that takes the ASCII representation of whatever that character is and turns it into a number. So we know that there should be a number in ASCII representation, which it would be. And it's going to set it to this RCX1. It's then going to create RDX5, which is the value that we just got times this constant. I don't know what the U is here, and then it's going to shift it to the right by 32, and shift it to the right by 3, and then subtract this. And so this is another situation where I think it's just a lot of time easier to go back to the disassembly. It just makes a little more sense, like looking at it step by step. But effectively what we're going to end up doing is we're going to end up walking this backwards and figuring out how to make this fall through to here. So we're taking the fifth and the sixth character, so right here and right here. Moving this to flag. We're taking those characters. We move the fifth character into EAX. We're getting that value and we're putting it at 2E. We're then moving the sixth character into EAX. We're getting that as a value and putting it into D. We're loading to E. So we're getting the fifth character, moving it into RIX. We're calling it A to I with that. So this is going to be a number, and we're going to get the value. It's going to get put into our EAX or RIX, and it's going to get put into here. And then 48 is going back into RIX. Plus 1. Doing multiplication, shift right. So if we go through all this and we look at it, basically what's going to end up happening is we're taking, we're subtracting EAX from ECX, and moving that into EDX, and then checking to see if they are the same number. And if they are, then we're jumping here. I'm going to get the breakpoint right there. So let's do these two. We know that one of these has to be a number. Let's make them both numbers because they seem to be doing math on it. So do like 1 and 2, just so that they're easy to spot. All right. So RIX is holding C. What? So 9, A, B, C, 9, 10. Yeah. Okay. So it's treating these as one number, and we are turning that into C. So hex C, which is 12, and it's in RIX. So we're moving that to 48. And this is just stuff is in the way, it's not a big deal. And then we're loading RAX plus 1 into ECX. So RCX you'll see is D because it is C plus 1. So we're going to move ECX into RIX, so taking the value here, moving it into here. And then we're going to multiply RIX times this big ass number and store it in RIX. So I'm going to single step that. We can verify the math here is correct. Times C what did it end up doing? I think it overflowed or something, and that's why it's different. But anyway, so we're going to shift RAX to the right by 32. So we get 2. Then we're going to move that into RDX. And we're going to shift that right by 3. And then we're going to move ECX and EAX. And keep going down here. And so now we're doing test EDX, EDX. So EDX right here. The reason. So we are taking it because it is non-zero. And so that's not what we want to do. We want to make sure that that value is going to be a 0 value for a non-zero value. So we can go back up here and like do the math, but Let me see if it has the better HLIL in here. So basically, we have to do this in reverse, and we figure out like what the values are. Um, So what this right here is doing is it's setting these up to make sure that they're one apart. And we can I'm going to skip this for right now, just because it's kind of irritating to figure this part out. One of the nice things that we can do is, because it doesn't drop out of the program, we can always come back to this. I know what the value is, but I don't want to do the math. It's just kind of irritating, and this is actually part of how I ended up doing this. Is I went down and I did some of the easier stuff first, and then came back. So I'm gonna move this back to HLIL. And we can look at some of the other portions of it, but that is the check right here. So we can move on to this. So this is the 7th character, and we just know that this is hex 40, which is the @ symbol. Fill this in. Oops, that is the wrong one. Grab the we'll swap these out with 1 and 2, because we know those are numbers. So it's 1, 2, 3, 4. All right, so we've got 2 numbers and an @ symbol, and we can verify this by grabbing this and dropping this into the debugger. and then we can go and we can examine here. So we see we have the first 4 set, because we know it's 8 GAT. These next 2, which were the ones we just skipped over, are not set. And then we have the next one here, which is the 7th one, and that is set. So that's the @ symbol. Moving down, we're coming into this loop here, and we see a whole bunch going on. And I'll do some renaming here. What did I just do? So this is our iterator. We're going to turn this into a decimal. So this is going to run 10 times. And if we look here, there's a whole bunch going on, but all it's doing is updating these A variables, like a bunch. And one of the things we can do is we can go down and look, and we're not actually ever using these. So most of this, like, we can skip over. What we actually care about is looking for places where those X variables are set. So we have the X08 here. We have the X07 here, X10 here. I think I'm missing one. 9. X9 is set here. And so we're setting I equal to 7. And part of the reason we're doing this, or the reason we're doing this, is that we want to skip over the first 7 characters that we've already read, because where it's going to pull the letter from is flag plus I, which is just like pointer math to get that. So this is our character right here. And this is the capital A. So all this is doing is it's taking the character and it's subtracting capital A off. And what this is going to do is give us the position in the alphabet, in the capital alphabet of these characters. So we're going to check to see if C is less than hex 19, which is what, 16 plus 9 is, I think, 26. 25. So 0 through 25 would be 26. So making sure that this is, A through Z. So if it's A through Z, then we're going to run a switch statement on it. And the ones that we care about are basically A, we care about whatever hex 17 is, there. X, so there's going to be 2 X's, because there's 2 that are set here, and there's one other one that we just missed. Where's the last X in here? We have, so 0, 8, and 0, 9. And here it is, 15. So if we go up and we change this, it's V. So we know 2 things here. One is this is telling us the letter that we care about is here. And this is telling us the position. So I equals 8. So for the x's, I is 9 or I is 10. And for v, I is 7. So that's going to be the 8th character, and then so the 8th character is v, the 9th character is a, and the 10th character is going to be x, and the 11th is x. So we can check this by we can check this by going back and grabbing the address. We'll just grab it from here. I don't want to say forms. Give me a regular. We'll grab this address here. We'll delete breakpoints, and we'll break there. And then we'll run this again. We hit the breakpoint. We can go inspect this, and we see that our initial 4 are set. The one for the @ is set, and then this is the one for the v, the a, the x, and the x. So we've made it through. And then if these are all set, then 6 gets set. I wonder if you don't actually need to be an @ then here. But yeah, it'll fail the check later. So we see that that gets set there, and if we look down a little bit further, we'll see that there's a CRC happening, and so that's probably why it matters, is so that the CRC matches. Yeah. So we're down here, and we are now checking the 11th character? Yeah, so the 11th character. So we need the 11th and the 12th character to equal hex 67. So we then equal hex 67, and then the 11th character minus the 12th character has to equal 1. So these two need to be exactly 1 apart from each other. So if we do hex 67 divided by 2 is 51. So it should be, let's just do this in decimal. It's much easier. It's 103. So 103 divided by 2 is 51. So it should be like 50, 52? Or 50... should be 52 and 51, which if we look at their character values is 4 and 3. And so we're going to subtract, so C is the first one, and it's getting subtracted. So we know that the order has to be, sorry, so C is the second one. So we know that the order has to be 3 and 4, so that the math works out. So they both together equal 67, 67, which is 103, and then the second one minus the first has to equal 1. So 4 minus 3 equals 1. So we're going to go down here then. We've figured out that this is 3 and 4. Let's update these. And we can grab this address here. We'll redo this. And we'll go and we'll check these. So this is our first 4, the 8 GAT, the 2 we haven't solved yet, @ V, A, X, X, 3, and 4. So we've made some good progress. We're getting through it. Moving on to the next one. So we're then grabbing the the 14th character D, and it is just 2E, which is dot. So that's pretty easy. We just know that that's dot. So it's looking like it is an email address. So at 8GAT something, 2 numbers at vax dot something. And we can hit this. We can go verify that that is also true. Did I not set the breakpoint? Why is that? Must be a bad address from here. This is what we want to check is right here. So this is it's moving into the X13, which is the 14th, because we're 0 and X. So all right, and we can now verify this. So 8GAT, 2 numbers we haven't solved yet. The @ V A X X dot 34 dot. Wait, do we already? No, I don't have a badge, but I'm all right. I'm glad to see it's cathartic and validating. Um, so 8 gat. We might have accidentally solved one of the other ones. Uh, 8 gat. The 12 we haven't solved at so v a x x 3 4 dot. Yep, we're good. Um, so oh, thanks. Oh, awesome. I didn't play the mud, but I heard a lot of people had a lot of fun on it. I was talking with some of the people that I think did really well on it. Babint. Um, so let's jump into the last few here. Um, so we're gonna rot 13 the next 2 characters and verify that they're 3D hex and hex 6. So basically, all we have to do is take these and reverse them by 13. So we'll just do 0 and x. Oh, and +1. So it would be +1. Wait, is that rot 13 the full thing? So then subtract. Let's just fix the 0 first. So that's 0, and then it's going to rot 13 the value +1. So we have to take 60, we go backwards 13, and then we subtract one more. R. Probably ORG. And we can verify these. 0 R. Well, I'll just put G in there for right now. Delete breakpoints. We'll do that. All right. And yeah, so we broke on that. Let's check these. So yeah, these are the 0 and the R. And so the last one is what we're going to check. And this is going in and it's reading that file, that temp file we created at the very beginning that it wrote a G to. So the last one is probably just going to be G. This again is P. We're going to get it here. So that's char. Then we're close the file. We remove the file from the system. And then we check C to make sure that it is the same thing. So we know that's going to be G because it's been written there, and that is that last part there. All right. So we can verify that last one there. All right. We'll break right here. And so we set all of these. The only ones we haven't set are those two numbers. And so that's all solved. I don't really feel like doing the last two, so we're just going to write a brute forcer for it because I'm lazy. We know it's gonna be numbers. It has to be those. So we'll just do. I think that the backticks will give us the output in Ruby. What was it? It was 8 get. I'm using this Ergo keyboard, and I haven't used it in a really long time, and I'm typing terribly. Where's the goals? And then it was what, success was the magic success. What's the one? 3? Where? Oh, we can just do I and J. I do something wrong? Oh. Yep, there we go. So get 35. We got it. That is the flag. So yeah, at only like 100 possible guesses, like it's significantly faster just to write the brute forcer than it is to go through and actually solve the math here. I'm still kind of sad that we didn't get the Angr script to work, but I can show that off real quick. Basically, this was what I set up, and if I had more memory allocated to this, probably, I don't know, it might work. But basically what it does is it spins up the program, and it creates a symbolic input that we're calling arg. It's 8 times 17 here, so 17 characters that are 8 bits each, so like 1 byte each. It's going to go through and apply constraints to every single one of those bytes. So we're going to say that it's a character, so it's somewhere between tilde and space, which is like hex 20, and then I think this is probably like somewhere around like 7F or something like that. Yeah, I think I probably did that too the first time I solved it. I just don't think it's worth doing it. Yeah, I mean that totally works too. Um, uh, but yeah, so you set up where you want to find. In this case, I don't have the rebased values in here, but I think that this points to like the success here, and then these are I think like the stack check fail, so making sure that it doesn't get down to there, and like right here, like where it prints fail, and then there's something else in there. I don't remember like what the other one was. But basically saying you don't want to avoid that. And it it ran out of memory before it solved it. I don't know if that's because for some reason there's just so much path explosion that it actually causes a problem, or if there's like issues with the actual like file being written. Like maybe it's not like maybe I need to create a symbolic file for that to work, and it doesn't understand like what's going on, or can't solve that constraint without specifying that. So I'm not sure. Something I'd like to spend more time with. I finally actually got Angr to spit out an answer for the Google CTF yesterday, and was shocked when it did, because everything I've thrown at it so far has just been like garbage. But yeah, that's the solution for this challenge, at least as far as I did it. But yeah. Uh, yeah, so the CRC stuff, uh, I think has to do with like I think the places where it can the CRC come into play are where, what was it? There was one of the things here we found where it had already been set, and then it yeah, it was the 6. So if you didn't get the at symbol, but you still got you still got the VAXX from here. This would still set 6, and so your CRC would fail. I don't know, because we brute forced it, and I actually didn't do the math here. This part also may have had a point where there needed to be there were multiple values that would have set the 4 and 5, but they only like one of them would pass CRC, or some of them would pass CRC. The rest of them were pretty straightforward, and I don't think there were alternative answers for them that would have come into play. I guess the other thing you could do is if you set a breakpoint on it or something, and you like updated the value that was in here, it could potentially like you could force this check to pass by changing the byte that's in the temp file, and then so your CRC would fail. But I mean, it's already setting up the value for you, and I don't see why you'd do that. Cool. Yeah. If there's no other questions, I'm just gonna wrap it up, and it's a quick 2-hour session, and let everyone get back to their Saturday. But I'm curious to know if anyone actually got this to work with Angr and got it solved that way, and like what it took to do that. So I'm definitely not an expert, with it, and I've just literally just got it to solve something for the first time yesterday. So I'm curious what would be required to make it work. Yep, you're welcome.